You are probably very familiar with carbohydrates. Carbohydrates are a large part of our diet, but we get carbohydrates in many forms. We can get these simple sugars, 1 or 2 monomers together, and they are very quick for us to break down. They're a fast source of energy for us. Complex carbohydrates, on the other hand, we look at being very large polymers that will take you a much longer time to break down. Now, this is not good or bad. We have to think about the needs of your body to understand why you may need simple sugars in one case and complex carbohydrates in other cases. So simple sugars, as we mentioned, sugars end in ose. So you see it here, a number of different sugars. We've talked about lactose now in our dairy products. Glucose, simple sugar. Ribose, part of your DNA. Sucrose is your basic table sugar, what you sprinkle on your cereal or in your coffee in the morning. And then fructose is actually our sugar associated with many fruits. So you can help you remember that that's associated with our fruits. Now, when we look at these different types of carbohydrates, those monomers that we talked about are those very simple sugars. We're going to put those together and build complex sugars. So we're going to build carbohydrates, or what we refer to as polysaccharides. So polysaccharide is just another name for a carbohydrate. So our monosaccharides that we talked about were glucose and fructose. And if we put those together, we're going to build a polysaccharide, or the general term, a carb. Okay? So when we continue to build these, and in most cases, you're going to put far more than 2 monomers together. Okay? Our monosaccharides here build these polysaccharides, but you're going to need many, many, many of these to truly build large, complex carbohydrates compared to our simple sugars, right? So when we look at our carbon skeletons in our monosaccharides, I'll show you a picture in just a moment, but we look at a number of different possibilities, but keep in mind that when we're talking about monosaccharides, we're talking about glucose, fructose, and a few others, but we're looking at only molecules that have less than 7 carbons in their skeletal system. This is important because in order for your body to burn simple sugars, to use simple sugars for energy, it has to be a simple sugar, meaning, in this case, less than 7 carbons. Okay, most of them, glucose that we look at, has 6 carbons. So we look at glucose, often just drawn like this. And we see that breaking this down is still going to take us a fair amount of work, but this is something your body is very equipped to do. So these monomers, as we mentioned, or the monosaccharides in this case, are typically in a ring form. We're going to look at more complex polysaccharides in a little bit that will form different types of structures, but this is the basic kind of structure for us. And like I said, most of us just draw it kind of as a quick 6-sided figure here. A disaccharide, di means 2, so that's just simply taking 2 glucose molecules, sticking them together and making maltose. We saw this before. But that's not where we end. Like I said, yes, technically this is a polymer, but it's not a very complex polymer. Your body can still deal with this very quickly. You would burn that sugar very, very quickly. If you wanted to talk about more long-term energy, we have to talk about a polysaccharide that is of some substance. And I have 4 examples here for you. Starch, that you're probably familiar with. Glycogen, which you may not have heard of before. Cellulose, again, probably familiar with. And chitin, may or may not have heard of before. Now, you see that these structures are much more complex than that 2-carbon ring polymer that I showed you a minute ago. In some cases, we're talking about the polymers being composed of thousands of monomers. So we have to think then, what is their function? Why are we putting so many monomers together? Because remember, to do this, we're going through all those dehydration reactions. We have to get these monomers to stick together. We've got to deal with that from an energetic perspective. So why would we do this? Well, for our polysaccharides, we see most of them used as storage or structural. These top two are storage. These bottom two are structural. So what we're looking at is, in the case of our structural polysaccharides, this very organized and distinct pattern. You can tell that these would stack together very easily. These others, the starch and the glycogen as storage molecules, very complex. You see, they probably don't stick together very well, but what we look for is these complex structures for long-term storage of sugar. So a plant stores sugar as starch. Who do you think stores sugar as glycogen? You do. And many animals. So that starch molecule that I mentioned to you, it is a polysaccharide and made up of glucose monomers. And typically, like I said, we see it in plants. So when you talk about something being starchy, that's what we mean. It literally is a polysaccharide of sugar, complex for storage in plants. Glycogen, storage in animals. The other characteristics are the same. It's a polysaccharide and it's made of glucose monomers. But we store glycogen. You actually store it in your liver. And we'll look at that more later on. Structural polysaccharides, I said, were the cellulose and the chitin. The cellulose we actually see in plant walls. This is important for support of the plant. Again, it's a polymer. You see that? Many monomers stuck together. Chitin, this is actually the structural sugar that is used to build exoskeletons in insects and crustaceans. So shrimp, right? All of that is made of chitin. It's just a complex sugar, complex carbohydrate, polysaccharide. It's all the same. So to build these, we're going to have to go through dehydration reactions every time you want to build them. So you can imagine that this is going to become fairly complex as a process to build these large macromolecules. But when they're needed, they're needed. So we have to go through this process. Now, as it stands, glucose sugars can be easily broken down in water, right? So we do look at polysaccharides as being hydrophilic or water-loving. We look at them as absorbing water. A good example of this would be like a cotton bath towel. When you dry off after the shower in the morning, you know that it's pretty good at absorbing water. Fine. Those bath towels with cotton are primarily made of cellulose. So very, very absorbent of water. It has other functions as well. What about fiber? Fiber is actually cellulose. You don't break it down very well, right? I told you it's very highly structured. That's its whole purpose, to give structure to a plant. You don't break it down very well. No animal does, really. So what we look at for cellulose or fiber, why are we so interested in it in our diet if it doesn't give us nutrition? Well, we talk about it as an intestinal scrub brush. Dietary fiber helps clean out your gastrointestinal tract and allows your GI tract to work more efficiently. Other things we have to consider, other weird things that go on, we look at things like Splenda. So Splenda says right here on the package, made from sugar. Is it? Actually, yes, it is. It is made from sugar. And it is actually chemically 600 times sweeter than sugar. That's crazy. So if it's made from sugar, how can it be so much sweeter than sugar and be no calories? What's different about it? 3 chlorines are actually put in place of 3 alcohol groups in the sugar. So when your body sees it, it doesn't recognize it as sugar. It's passed out of your body. But you still taste it as sweet in the taste buds on your tongue. But it's not metabolized, so you get no calories from it. Now, there are many people that think that these artificial sweeteners are actually kind of dangerous for us in other ways because of these chemical substitutions. Some folks just think it's better living through chemistry. You decide.